Hi guys, I hope you're doing well. The basic point of this video is to help you guys review the two kind of circuits that we've been looking at so far. So to remind you guys, we've been looking at parallel circuits and series circuits. Now, a series circuit is the simplest sort of circuit we can imagine. In a series circuit, electricity flows in one continuous path all the way from one side of a battery through a set of wires or other conductors to the other side of the battery. Now, as things flow through that circuit, all of the electricity is following the exact same path. So at any point along the circuit, the amount of electricity that's flowing, what we call the current is going to be the same at any point because the electricity that's going through one part of the circuit has got to be the same as the electricity that's flowing through the other part of the circuit. Now in a parallel circuit, things are a little more complicated. In a parallel circuit, there are many paths that the electricity can choose from. Now, the electricity can choose to go through one of several different paths to get from one side of the battery to the other and complete the circuit. Now, the amount of electricity that goes through each path, the current, that's something that we can calculate, but it's not going to be the same. In different paths, there's going to be a different amount of electricity that goes through. The harder the path is to follow, in other words, the higher the resistance, the less electricity is going to go through. Now, if you'll remember, in class we talked about ways that we could calculate the amount of current, voltage, and resistance in different circuits. What I'd like to do now is to look at these two circuits and see how we could calculate voltage, current, and resistance in both of them. All right, so let's take a look at a circuit like this one. Now, in this circuit, we have three resistors, shown again by our little zigzaggy wire. Here's R1, R2, and R3. We could number them in any order we want. Now, this represents our battery with its two terminals. Let's say that our battery has a voltage of 9 volts. Now, if we take a look at our resistors in this series circuit, electricity is going to have to pass through each one in turn. There's not going to be any opportunity for the electricity to skip and get back to the battery without going through all three of the resistors. So what I want to do is give you guys an opportunity to track through and figure out what our current might be based on different resistances. So let's say, for example, that we know the resistance of each one of these resistors. Let's say that R1 is going to be 3 ohms. And R2 is going to be 2 ohms. And R3, we're going to say that this one is going to be 4 ohms. Now, we know that in a series circuit, the total resistance is simply the sum of the resistance of each individual resistor. So our total resistance is going to, in this case, be 9 ohms. Now, we can figure out the current at any point in this circuit by remembering that V is equal to IR. This is always how I remember this equation. Now, yes, we can solve it for any part. So in this case, we know R and we know V, and what we're trying to figure out is I. So let's rearrange for I. Let's divide both sides by R, and I get that I is equal to V over R. Now, if I substituting in 9 volts and 9 ohms, I can pretty quickly see that I is going to be 9 over 9, or 1 amp. Now, let's look at this in a slightly different way. I've redrawn the exact same circuit, just labeling our resistances. Now, let's take a look at what our resistance in each of these locations is going to be, what our current in each location will be, and what our voltage drop in each location will be. Now, we know that overall, we have a voltage drop of 9 volts. from the time we leave the battery to the time we get back to the battery, our current is going to drop 9 volts in terms of its energy, because that's the boost in potential energy that the battery is supplying, 9 volts. Now, we figured out previously that our current at every point is going to be 1 amp. So we've got 1 amp of current in every location. And in each case, we know our resistance. We know R1 is going to be 3 ohms. We know R2 is going to be 2 ohms. And we know R3 is going to be 4 ohms. So overall, we've got 9 ohms of resistance. Now, here's where it gets a little bit tricky. We have to be able to figure out the voltage drop that occurs at every one of these resistors. Now, keep in mind that it's always the case that V is equal to I times R. So if we look, we could say for resistor 1 right here, where we have a 3 ohm resistance and 1 amp of current, we could look and try to find what the voltage is. So we say voltage is current times resistance, 1 times 3. Well, our voltage is going to be 3 volts. 1 amp times 3 ohms. Our voltage for the second one, here, we're going to see a voltage drop of 2 volts. 1 amp times 2 ohms. And for the fourth one, 4 volts. 1 amp times 4 ohms. Now in this case, it's always just the same as the resistance, but you can see that isn't always going to be the case. If our current were 2 amps, hey, now 2 amps times 3 ohms, we'd end up with a voltage drop of 6 volts as we went across that resistor. So in this particular case, it simply is 1, but that's just a fluke of the current being 1. So now let's take a look at a parallel circuit. In this circuit, when electricity flows out of our battery, it can take one of 3 different paths to get back to the battery. It doesn't have to, and in fact it won't, go through all 3. If I start here, I could go through our 3 ohm resistor and get back to the battery. I could go through the 2 ohm resistor and get back to the battery. I could go through the 4 ohm resistor and get back to the battery. I wouldn't be going through one and then the other before I get to the battery. I wouldn't come up here through the 3 ohm and then through the 2 ohm and then through the 4 ohm and come back to the battery. That simply wouldn't happen. It's going to be one of these 3 parallel paths. Now, if we take a look at calculating the resistance, here, it's not going to simply be a case of adding up the resistances of all of the different paths. What we're going to say is that in a parallel circuit, our total resistance, our total, 1 over that, is going to equal 1 over each of the individual resistances. So in this case, 1 over R1 plus 1 over R2 plus 1 over R3. So if we look here, we could say 1 over our R total is going to be 1 over 3 plus 1 over 2 plus 1 over 4. Now, in order to add up these fractions, we've got to find a common multiple. 2 and 3, we could go with 6, but 4 doesn't go so well into that, so let's take it out to 12. We could find that 1 over R total is going to be, well, 1/3 is the same as 4/12. 1/2 is the same as 6/12. And 1/4 is the same as 3/12. So if we look at 1 over R total, that's going to be equal to 4 and 6 is 10, plus 3 is 13, 13/12. So our total is simply going to be 12 over 13 ohms. Notice how different that is from the case with a series circuit. If that series circuit, if we had to go through each one of these resistors in turn, we'd end up with a resistance of 9 ohms. Here, we have a resistance overall of just less than 1 ohm. But now, let's see if we can calculate the amount of current and voltage in each pathway. So if we do a VIR chart for each case, our first resistor, remember, is going to be 3 ohms. Our second one is going to be 2 ohms. Our last one is going to be 4 ohms. And our total is going to end up being 12 over 13 ohms. I'm just going to adjust the camera so we can see that a little bit more clearly. Now, let's take a look. Again, remembering that in each case, V equals IR. Now, the thing about a parallel circuit is that we know the voltage through any one of these paths is going to be the same. So if our total voltage is 9 volts, we know our voltage at any point is going to be 9 volts, our voltage through any one of these 3 paths. So what we're left to do is to try to figure out the current in each one. Now keep in mind, V is IR. Rearranging this, I is going to be V divided by R. So if we looked at the amount of current that flows through our first path, here through our 3 ohm resistor, we could say that I, the current, is going to be the voltage divided by the resistance. That's going to be 3 amps. Now that kind of makes sense, because if we look at this, the more voltage, the more current, right? That makes sense. The more resistance, the less current. Electricity isn't going to try to flow through the path that has the most resistance. So let me ask you guys, of these 3 paths, 3 ohms, 2 ohms, and 4 ohms, where's electricity going to want to go? Hopefully, you recognize, yeah, it wants to take the path literally of least resistance. The most electricity is going to go through here with 2 ohms. So as we do this, that's always a good way to double check. Let's take a look here. If our resistance is 2 ohms, our voltage is 9, well, we're saying current is voltage divided by resistance. Well, 9 divided by 2 is going to be 4.5. Now, in this last case, we should see the least amount of current flowing through our most resistant path. So 9 divided by our resistance here, which is 4. 9 divided by 4, well, we're just going to write that as 9/4 amps. You could obviously plug this into your calculator and get a fraction. It's going to look like 2.25 amps. So the idea is that our flow through any one of these is going to be a little bit different. So hopefully by taking a look at those examples, you'll see how we could calculate the amount of current going through any path in a parallel circuit, or calculate the voltage drop through any of the resistors in a series circuit. Now, I think a very legitimate question to ask anytime you're doing anything in science is, so what? Why would I want to do this? Yes, it's kind of interesting mathematically to be able to just go through and say, oh gosh, I could figure this out, but why would we care? Well, if I'm looking at how much current is actually going to flow through any part of a parallel circuit, that might be important if I'm trying to figure out, could I run something on this parallel circuit? Do I have enough current flowing through that circuit to light a light bulb? Do I have enough current flowing through that to make my saw work? Whatever it is you're trying to do, you might care about this. Whether you're trying to wire a house or whether you're simply trying to make a bunch of Christmas lights work. I hope you found this review useful, and I hope you realize that you can refer back to it at any time as you're working on the homework. If you have questions that go beyond this, or you simply want something explained in a different way, you can always contact me or Donna via email or at office hours. Take care, guys. Hope you're doing well.